Good afternoon, everybody. Before I start, I want to thank the organizers for the invitation to this wonderful workshop. I'm very excited to be here and talk about the latest research that I did together with Dr. Reinhard Maurer at the University of Warwick, where we developed machine learning models to fit orbital energies and excited states of functional organic molecules. Before I start, I want to introduce you to the importance of excited state simulations by making you think what would happen if there was no light. And I believe that we could come up all with at least one thing that would not exist without light excitation. Take, for instance, photosynthesis, human vision with the eye, or phototherapy. But there are also negative side effects of light-induced reactions, such as skin cancer and skin alteration, bleaching, or blindness. And if we want to understand why some processes are harmful and why some others are not, we need to understand why molecules are photostable or not. So we can do this by doing experiments and theoretical simulations. So with theoretical simulations, we could find out about the exact mechanisms that take place after light excitation. And by knowing about these excited state processes, we can use the information to design new molecules with tailored optoelectronics and excited state properties, and use this information further to develop new functional organic materials. But there is one problem to excited state simulations. So if we consider a molecule and we want to compute energies and some other properties, then this is usually quite expensive. So accurate methods are limited to very small systems. And this is even more severe for excited state simulations because we do not only need to compute one potential energy surface, but we need to compute more potential energy surfaces. So we have more energies because we have the ground state and the excited state energies, and we have the dipole moments for every state that we want to compute. So this is a very nice place where machine learning can advance the research field. So with machine learning, we would learn quantum chemistry. So we would learn the energy, the dipole moments, and we can then make a prediction extremely fast. So instead of many CPU hours, the simulation would take only a few milliseconds. So where can machine learning actually help? So if we do excited state simulation, then there are several inputs that we need to consider. For instance, for multi-reference method, we need to choose an active space. If we do a DFT simulation, we need to choose a density functional. And machine learning could help at this place. And then there is the primary output, which is a fundamental property of any simulation. This would be the density or the wave function. So if we learn the wave function, then we could solve the Schrödinger equation, and we can derive from that the energy, the dipole moment, or the non-adiabatic couplings, which are all very important. On the other hand, we could also directly learn the secondary outputs, which is directly learning the energy or the dipole moments. And once we have these values, we could use this information to predict absorption spectra, for instance, which would be the tertiary output. But of course, again, we can also learn the tertiary output directly. And in the end, we could also use machine learning to interpret our results via clustering, for instance. So the focus in this talk will be on the primary and the secondary output because it's most powerful to have these. So what we did so far with machine learning for excited state was that we used machine learning to accelerate non-adiabatic dynamics. For instance, we showed for small organic molecules that it's possible to go beyond timescales of conventional methods, obtaining better statistics. And in the future, we also want to simulate more complex systems such as amino acids or functional organic inorganic molecules. And in this talk, I'm going to focus on spectroscopy. So we have already shown that machine learning can help to simulate UV visible absorption spectra. And today I'm going to talk about photoemission spectroscopy. So what is our problem? I'm going to introduce you to the problem with fluorine. Fluorine is now the star of the presentation. And it is very important because it is an important molecule in optoelectronics due to its special optoelectronic properties. But it's not the only molecule that is important. There is also phenanthroine, which differs to fluorine by only one carbon atom, yet it exhibits different optoelectronic properties. And there are many more molecules that are important, such as members of the azine family. And dependent on who you ask, you might end up with about 10 to the power of 20 to 10 to the power of 60 organic molecules that are of potential relevance to the research field of optoelectronics. And now imagine you want to develop a new functional organic material and you want to search for the molecule that has the most optimal properties for this purpose. You might end up with searching for a needle in a haystack. So this seems like an almost impossible task. But if we have only a certain amount of molecules, we could characterize the optoelectronic properties of molecules with photoelectron spectroscopy. So with photoelectron spectroscopy, we perturb a system via light. So there is photoemission, for instance, where we can probe the occupied states of a molecule. So here we have all the occupied orbitals where the electrons are filled. Here we have the unoccupied orbitals. Let me take it. So here we have the occupied, here we have the unoccupied orbitals, and then we shine light onto the system. And we can then probe the occupied states via an electron that is ejected. So we have the kinetic energy, we have the work function of the material, and we have the energy that enters. And with this, we can compute the ionization potential, which is equal to the HOMO energy, the orbital energy that is probed. On the other hand, we can also use inverse photoemission spectroscopy, where we can probe the unoccupied states. So in this case, the electron is not ejected, but the electron is added to the system. So we would then get the negative of the electron affinity, which is equal to the energy of the orbital that is probed. There are two ways to do photoelectron spectroscopy. So the first one would be to do it via experiment. This would mean that we have a molecule, select a molecule that we want to investigate, then we have to go to the lab, we have to buy the chemical, synthesize the molecule, or maybe buy the molecule, and then we measure it. But unfortunately, as you can remember from your previous study, that this is quite time consuming, it is expensive, it is dangerous if the chemicals are toxic, and we don't know if the molecule that we are interested in is synthesizable. And this is a very good place where theory can help a lot. So with theory, we can simulate photoemission spectra and we can complement experiment. And what is very important here is that we can simulate the spectra of many molecules before we have to go to the lab and synthesize them and measure them. So we can use this information to design new molecules and to find very important molecules. And unfortunately, high throughput screening with high accuracy methods is also limited because it is way too expensive. So this is now the place where machine learning comes in, because with machine learning, we could learn the orbital energies or the excited states, predict photoemission spectra extremely fast, and enable high throughput screening to find new organic molecules with special optoelectronic properties. So what did we do exactly? Because it is a machine learning workshop, I think I don't have to explain to you what machine learning is. But very briefly, we used a neural network to find the best relation between a molecular geometry and the targeted outputs, which would be the excited state energies in this case. And as you might also know, we have so-called fitting parameters in our networks. This would be the weight, and they connect the nodes within a network. And we can find these values by using a training set which contains the molecular geometries, in this case, of many different diverse functional organic molecules, and also the different energy levels that we want to fit. So once we have the fitting parameters, we can then plug it into the network and get our output that we want. So just a short reminder, I will focus on the primary outputs and the secondary outputs. So what are these for spectroscopy? So the primary output in photoelectron spectroscopy would be the Hamiltonian in the local orbital representation. So we have our Hamiltonian, and if we diagonalize it, we get the orbital energies, and we can then use the orbital energies here to get our spectrum by via Gaussian convolution, for instance, or convolution with any line-shaped function. Unfortunately, predicting the primary output, so the Hamiltonian, has yet only been shown for one system, and we want to simulate many different molecules and advance high throughput screening. So at the moment, this was not shown to work. So people rather focus on fitting the excited states directly, so the secondary output. And with this information, we could still find out which orbital energy gives rise to which peak. And the last possibility or option would be to predict the tertiary output, which would be the spectral shape. So we could discretize the spectrum into like 100 values and learn these. But unfortunately, in this case, we lose the interpretability. So we wanted to go to the primary or secondary output, and that's exactly what we did. So we tried to fit the orbital energies of organic molecules, and we used a spectroscopy data set that was especially developed to advance the research field of optoelectronics. And this is called the OE62 spectroscopy dataset. So it contains orbital energies at the DFT PBE plus van der Waals level of theory. So it contains a lot of diverse molecules, which you can also see here. So it contains very small molecules with molecules up to like 180 atoms. And it also has a very rich chemical diversity inside, so many different elements. So this is quite difficult to fit. And unfortunately, fitting the orbital energies directly was not possible in our case because there was just simply not enough data. We wanted to fit hundreds of orbital energies for different molecules, and we had 62,000 data points, which was not enough. So therefore, we try to find a more meaningful machine learning model which could learn from little data. So how is this possible? We know that the logarithm of the prediction accuracy and the number of data points is linear. So with a conventional machine learning model and some available data, we might get this accuracy. But if we want to have higher accuracy, then we run into a problem. And it is known that the accuracy of a machine learning model can be increased by introducing physics into the model. So by developing a physically inspired model, we could get away with the same amount of data points, but might reach the desired accuracy. So that's exactly what we did. And our approach is a latent machine learning Hamiltonian, which is now called SchNet+H. And you can see the concept and the architecture of our network here. So we have again the input, we have the hidden layers, and now we adapted the last layer such that it represents a Hamiltonian matrix. And after diagonalization of this matrix, it gives us the orbital energy, such as this is done in quantum chemistry. But the Hamiltonian does not have any physical meaning. So we fit different molecules of different sizes. And now it is important to know that every molecule has a different number of electrons, and thus it has a different number of orbital energies. Consider only hydrogen. Hydrogen has the 1s orbital and 1 electron. If we have a very large molecule, then we have different p orbitals, we might have d orbitals, and we might have hundreds of thousands of them. So how can a model predict orbital energies of different molecules with different sizes? So this was the main question that we had to address at this point. And we developed the Hamiltonian in a way that it has a fixed size. So we fixed the position of the HOMO orbital and the LUMO orbital. So the highest occupied molecular orbital up to here, the orbitals are filled with electrons, and from the lowest unoccupied molecular orbital on, the orbital energies are not filled with electrons anymore. And we define an energy range that we fit, so we go a few electron volts below the HOMO and a few electron volts above the LUMO and fit only these values. And if a molecule doesn't have the number of orbital energies that we represent in the matrix, then we use a mask and do not fit these values. So this can be seen as a machine learning basis for the orbital energies. Again, diagonalization of this basis gives us the orbital energies. We have a fixed energy range and of course also a varying number of orbital energies that we fit. So after developing this approach, we wanted to investigate whether our model is better than the existing models. And indeed, there do exist machine learning models for the excited states. So the simplest approach would be a single state model, which means that for every orbital energy, for every excited state that we want to learn, we have one machine learning model. So this works quite well because we just fit one value. But we require many models. And except for the HOMO and the LUMO, this is not transferable because if we have a machine learning model for the third excited state, for the 2b orbital, for instance, and our molecule doesn't have this orbital, then it might run into a problem. The other possibility is to use a multi-state machine learning model, which means that, again, we would fit the orbital energies directly, but in one model. So this is unfortunately also only partly transferable. We have chosen the water molecule as our test system because it is simple, and we decided to fit 18 orbital energies. So here you can see the results. In light blue, you can see the scatter plot, which shows the machine learning predicted orbital energies against the reference orbital energies. And this is the single state model. So we have 18 single state models. Here is the model for the HOMO and the LUMO orbital energies. And you can see that it fits quite well. And if we then use our multi-state model, which fits all orbital energies at once, you can see that it diverges more compared to, so the model is not that accurate. And if we zoom in to the HOMO and the LUMO, which are the most important orbital energies, then you can see that the scatter plot is quite off. And this is a problem because there are errors up to 400 millieV per orbital energies, which is quite large. And if it doesn't work for such small systems, then it might be very problematic for complex systems. So we then compare to our SchNet+H model, and you can see the results in dark blue. So what you can see is that the model is more accurate than the multi-state model. And if we zoom in, then the HOMO and the LUMO is much better represented. So in fact, our model is better than the multi-state model that is already existing. We also computed a learning curve. So you can see here that the offset, so the error that we get for very small amount of data points is already lower. And also the learning behavior is slightly better. So the accuracy decreases faster. And we wanted to investigate whether this is only true for other molecules. So we trained on a database which contains ethanol molecules. And there were 30,000 data points from molecular dynamic simulations. You can see the results and scatter plot here. In dark blue, you can always see the worst predicted molecule in the test set. And you can also see a picture of the worst predicted molecule. So it works quite well. Then we have chosen the QM9 database, which is a data set and that contains 134,000 organic molecules with up to 4 non-hydrogen atoms. So it is more challenging than only water or ethanol, but it only contains equilibrium geometries. So you can see the scatter plot here. It is worse than before. This is the worst predicted molecule, a 4-membered ring attached to a 5-membered ring. So quite complex and not very common, but it also worked. So with this, and last but not least, we wanted to investigate whether we can predict different molecules and different conformations of these molecules. So we investigated this with the QM7X database, which contains up to 4.2 million data points of diverse molecules. And you can see the scatter plots here. And this is again the diverse predicted molecule, which already shows fragmentation during the dynamics. We, of course, wanted to know why this works so well, because we just put a latent Hamiltonian matrix into our network, which doesn't have any physical meaning besides the orbital energies being the eigenvalues of this matrix. So we have chosen a reaction coordinate along a molecular dynamics trajectory from the QM7X dataset, and we plotted the occupied orbital energies and the unoccupied orbital energies. And what you can see is that there are several regions along the conformational space that have some kind of avoided crossing, so the curves are not smooth at this point. And this is problematic because machine learning is not very good at fitting non-smooth functions because there are smooth functions by definition. Therefore, we also plot the diagonal matrix elements along the same reaction coordinate. So the off-diagonal matrix elements look very similar. And you can see that the same curves here, they are allowed to cross compared to before. And because we allow them to cross, we can fit smooth functions and outsource the problem of non-smooth properties from the actual fitting process. So this is what our network would look like now. So we have our input, the molecular geometry. We have the usual neural network, and the last layer then represents a latent Hamiltonian. After diagonalization, it gives us the orbital energies as the eigenvalues. So this latent Hamiltonian is smooth, whereas the energies are not. So we outsource our problem. And we then investigated the performance of our model on the OE62 training set, which was the actual purpose why we developed it. And we did it, and you can see here the results. This is the scatter plot. So you can see that it is, of course, worse than it was before because we have little data, and the training set is also contains very many diverse large molecules. And there is an outlier, which you can see is here is a very complex molecule with an 8-membered nitrogen cage, which is also not very common. But in principle, we were quite happy with the results. And then we used the orbital energies to predict the photoemission spectra via Gaussian convolution. So you can see here also the peak out that corresponds to the unoccupied state. And we then compare to experiment. And what you can see is that the experimental values didn't fit our predicted spectrum. And we were quite disappointed because we now have a model with which we can fit orbital energies of important molecules, but now the accuracy of the reference data is not good enough. And fortunately, this training set also contains a smaller subset of 5,000 data points at the GW level of theory. So what is the GW approximation? The GW approximation can correct the DFT orbital energies that are underestimated due to the neglect of the self-interaction energy. So in DFT, the electrons are assumed to be non-interacting, and this can be corrected with GW. So the data is based on G0 W0, which is a single shot perturbation, where the perturbation is the electron that is ejected or added. So what we obtain in the end are not orbital energies, but we obtain quasi-particle energies that should be comparable to experiments. So we have 5,000 data points, and again, we wanted to do machine learning to fit these 5,000 data points. And before we had 62,000, so obviously 5,000 data points are not enough. And we went back to our previous plot where we know that if we have physically inspired models, we can get away with little data, but we wanted to get now away with even less data points. So we now don't have 62,000 data points, but we have 5,000, and now we have a problem again. So we know that we can use an approach which is called delta machine learning, which learns the delta between two different methods. So the method should be similar. And in our case, this would be the difference between DFT and GW. And our model only learns this difference. So we get then the orbital energies at the GW approximation by using the orbital energies that we obtained from our physical inspired machine learning model, plus the orbital energies that we obtained from a delta machine learning model, which learns the difference between the DFT and the GW values. So we fit the first model on the orbital energies at the DFT level of theory, and then we fit the second neural network on the difference between neural network 1 and GW to obtain quasi-particle energies. So you can see here the result of the scatter plot in dark blue. These are the GW values, and you can see that they look better than before. And last but not least, we then used this model on top of the photoemission spectrum of fluorine that we had before. And you can see here the photoemission spectrum that we obtained with the first neural network and the second one. And if we compare to experiment, we can see that the photoemission spectrum based on GW fits the experimental value much better, and it is burned. So we took a look at phenanthine, which was also introduced, that only differs by this one carbon atom here. And we again predict the spectrum at the with our first machine learning model. You can see again it doesn't fit to experiment. And if we put the second machine learning model on top and correct the orbital energies to quasi-particle energies, we get a spectrum that is comparable to experiment. So we also wanted to investigate whether we can predict members of the azine family, so molecules with different conjugation lengths. And so here we have only one ring, then this would be benzene, naphthalene, anthracene, tetrazene up to a 6-membered ring. And you can see in dark blue the electron affinities and the ionization potentials predicted by our model, and in orange the values based on experiment. So you can see that our model slightly underestimates the ionization potential and the electron affinities, but this is not an artifact of the machine learning model. In fact, it is well known that GW cannot underestimate these systems a little bit. And what is also very nice is that we could predict the electron affinity of the 6-membered ring, which was not possible in experiment due to instabilities of the system. So with this, I already come to a conclusion. So I hope that I could show you that we developed a machine learning model to predict orbital energies and quasi-particle energies, which was possible with a physically inspired model and a delta machine learning approach. So we can fit now many diverse molecules, and in the future, we want to complement photoemission spectra and do high throughput screening. So we want to screen many different molecules and find new molecules with special optoelectronic properties. So the presented work, if you're more interested into it, was recently accepted at Chemical Science. And if you want to know more about machine learning and computational chemistry, we have recently written a perspective that was published in JCP. And also very recently, we did a review for machine learning for excited states in Chemical Reviews. And with this, I want to thank you for your attention. I want to thank my current research group at the University of Warwick, Professor Dr. Reinhard Maurer, and two collaborators, Michael Gastecker and Christoph Schütt. So thanks